All right. Glad I saw that. All right, so I'm going to switch over to my iPad. Let's see. All right. So number 23 in section 1.1. This is 1.1, number 23. And we're given this matrix. And let's see, so the directions say determine the value or values of H such that the matrix is the augmented matrix of a consistent linear system. So they're telling us this is an augmented matrix. So I'm going to draw a line there just so that can will remind us we're working with an augmented matrix here. And they want to know what values of H will make this a consistent linear system. So we need to remember or think back to on Monday. And so we need to know, what does consistent mean? Anybody remember what consistent means?
It has at least one solution.
Has at least one solution, yes. Has at least one solution, right. Okay, so, and the way that we know a system is consistent is that it's not inconsistent. All right, so that sounds a little bit strange, but that's actually the way to determine that. So we know that a system is inconsistent if in echelon form, the augmented matrix has a row of the form. You remember what that form is?
All zeros, and then the augmented no zero was not a zero.
Exactly. So we've got all zeros, 0, 0, right? So all zeros, and then in the augmented column, not zero. Okay. So so basically these are the two facts we're going to use to answer this question. So yeah. All right. So first thing we need to do is put that matrix in echelon form. So what's the first thing we look for when we're doing that?
Bottom rows to be zeros.
Zero.
The stair pattern.
Yeah. So yeah, you guys are on the right track. We need to we start up here in the upper left, right? And we want to get a non-zero value there if we can. And we already have one, so we're done with that part. Then once we have that non-zero value, if that's possible, then we want to zero out underneath. So what we want to do here is we want to zero out this position. All right. So to zero that one out, we need to do a row operation. So we need to figure out, we got to multiply something times 1, add it to 3 and get 0. So clearly that's -3, right? So we're going to multiply -3 times row 1, add that to row 2, and that will give us a 0 under the 1. So the first row is not changing. All right, so it still looks like that. Second row is, we're going to get a 0 there. We're going to have -3 times h plus 6. So we just leave that like it is, -3 times h plus 6. And then we're going to have -3 times 4 is -12 plus 8 is -4. All right, that look right? All right, now at this point, the matrix is in echelon form. So if you remember the rules, right? So one rule is if there's any rows of zeros, they're at the bottom. We don't have any rows of zeros. If we have where we have a leading entry, we zero out below it. And so we have a leading entry here and we've zeroed out below it. This thing here could be a leading entry depending on the value of h, but there's nothing below it, so we don't need to worry. And then the other rule is that you have that staircase structure, right? So you got your leading entry here, you move over and down and have your next leading entry. All right, so we satisfy that. The rule is every leading entry is to the right of the one in the previous row. So here's a leading entry in the next row. All right, the leading entry moves to the right. Okay, so this matrix is an echelon form. We just want to go back to this, right? So the problem asks what values of h will make the system consistent. And so it means, so we want to look at, values of h that don't give us this sort of thing. So when you think about that, what do you see? Any thoughts? When I look at it, I see.
If h equals 2, then it would be inconsistent.
Yeah. So if you look, we can't do anything about that 0. And I look over here and I say, oh, we've got this non-zero value on the right. So we got to make sure that this thing here is not 0, right? So we want -3h plus 6 to not equal 0, which means that what? H is not equal to 2, right? Yeah. So there's your answer. H is not equal to 2. Because the system is either consistent or it's inconsistent. And for this system to be inconsistent, this would need to be a 0, which happens when h is 2. So we don't want h to be 2. Questions on that?
Helps. Thank you.
Yeah, sure. These are like 23, 24, 25, 26. Those are great problems. I can guarantee you will see one like that on the quiz Monday.
So the answer would be anything except 2.
Yep, the answer, I mean, that's what I would write for the answer. H not equal to 2. All right, so how about other questions? Let me see. So well, let's see another one. Oops. Okay. Are we back? Guess my screen go black and then come back.
We can see the screen.
You can?
Yeah.
Okay. All right. Okay. This thing seems to be very my connection seems to be a little touchy here, but okay, so I'm going to go on. Let's look. It's still in section 1.1, number 37. So it says gives you this system. So it looks like x1 plus 3x2 equals f, and cx1 plus dx2 equals g. And it says, suppose this system below is consistent for all possible values of f and g. What can you say about c and d? So the problem tells us this system is always consistent. So it's saying, what does that tell us about c and d? So again, we approach it the same way we did the previous problem, where we're gonna put it in a matrix. It's gonna look like this. And we're gonna put this in echelon form. All right, so so in this case, right, it's just like this previous one, really. You know, we had a 3 here that we wanted to zero out. Same thing here, we got a, except it's c, that we got to zero out. And maybe I should just say a little bit about, you know, one thing that you're probably accustomed to is using variables like x and y and z and so forth. In this course, we transition away from that pretty quickly, even in section 1.1, and start using variables like x1 and x2, and if we have more, x3, x4, x5 with these subscripts. And that's just because we want to be able to talk about an arbitrary number of variables. And so so instead of giving them all different letters to represent them, we just use subscripts on x typically. So just a FYI there. All right, so so if I want to do row operation here, it's the same idea as before. I'm going to multiply row 1 by negative c, add that to row 2. So row 1 again doesn't change. In row 2, right? So I'm going to get 0 there. And then I've got what? I got a negative c times 3 plus d. So negative 3c plus d here. And then I got the c, negative c times f, so negative c times f plus g here. Everybody good with that? And then again, just like up in the problem above, we're now, right, we're now in echelon form, right? So this is right, we're in echelon form here. And so, so let's think about this. Whoops, wrong color. Okay, so if it's always consistent, always consistent means that that there's no row of the form 0, 0, not 0. Okay, so that tells us that negative 3c plus d is not equal to 0, right? Because it, now how do we know that? It's because in the problem it says that this system is always consistent. So always consistent means it doesn't matter what f and g are, right? They has to work, has to be consistent no matter what they are. So clearly there are going to be cases where this thing here is not 0. And we can come up with since it has to be true for all possible values of f and g, clearly this could be not equal to 0. So that means that that for us to have no row of this form, it means that we have to assume that negative 3c plus d is not 0. And so, so that's it, actually. That's it. It says, what can you assume about C and D? Well, we can assume this, that -3C plus D is not equal to 0. Questions on that? All right. Okay, let's move on. Let's see. Any questions from section 1.2? Okay, I can see that there's a little bit in 1.2 we didn't specifically talk about last time. So let's do that. So let's see. So I'm looking at like question or problems 7 through 13-ish. They say to find the general form of the solution. Let's look at one of those. All right, so moving here to section 1.2. Let's just look at number 12 here, problem 12. So we start off with this matrix. Okay, so and the instructions say to find the general form of the solution. And it says this is an augmented matrix, so I'm going to draw this line just so we're clear on that. Okay, so find the general form of the solution. So one thing that we can know right away just by looking at this problem is that since we've got more variables than we have equations. So if the system is consistent, it's going to have an infinite number of solutions because we've got more variables than equations. All right, so but to figure that out, we have to do some row operations, put this matrix in echelon form. So let's work through that. So tell me, what's the first row operation I should do here?
Find the leading entries.
Yep. So let's see, I'm gonna start up in the upper left. I've got a leading entry here. So that's good. Then what do I do?
Would you swap the second and third?
Well, let's think a little bit. What do I want to accomplish? Let's instead of like what specific operation should I do? What do I want to accomplish? What's like the next step I want to accomplish?
Do you try to get rid of the -1?
Yeah. So
Bottom row.
yeah. So so I always think in terms of find your leading entry or establish a leading entry if possible, which we have right here. And then you want to zero out underneath that. So we want to zero out, right? So we already got a 0 here, which is nice. It's less work for us to do, but we don't have a 0 here. So that's what we want to work on. So we want to zero that out. All right. So to do that, we're going to change that row, which means we're not going to change the first 2 rows. So I'm going to just write those down. All right, and so what row operation do I need to do to get a 0 there in that third row?
Nothing.
What?
Just add row 1 to row 3.
Yes. So always, so you always want to establish your leading entry, and then that's the value that you're going to use to zero out in that column. So yeah, so we want to, so basically we're saying, what do I need to multiply by 1 such that when I add it to -1, I get 0? Well, that's a pretty easy question, right? So 1 times row 1 plus row 3, which, is basically just adding those rows together. -4, 6 and 2 is 8, 12. All right. So, so this is nice, right? We've got our leading entry and we've zeroed out below it. And then, so then we want to move over and find our next leading entry. And so I move over and down, but, I don't have, there's no non-zero values left to be a leading entry in this column. So I just keep on going. I go over and I find this 1, and this 1 here is going to be my next leading entry. So this column here is not going to have a leading entry. And I think I talked about this just a little bit last time, but when you have a column that doesn't have a leading entry, then that's how you know you've got an infinite number of solutions, assuming the system's consistent. And I'll talk about that a little more in just a minute. All right, so at this point, I've got my leading entry here, and I need to zero out below it. All right, so same thing as we did earlier. All right, want to zero out that guy. So to do that, I need to do another row operation. So what row operation do I do at this point? And again, at this, before we go to that, right, I'm not changing rows 1 or 2, so I just rewrite those. And so what row operation do I need to do to make that -4 a 0?
4R2 plus row 3.
Yep. And again, remember I said, find your leading entry and use it to zero out. So we're going to basically say, what do I need to multiply by 1 such that when I add to -4, I get 0? And so clearly that's 4. So 4 times row 2 plus row 3. And I get 0, 0, 0. And then what? I got 4 times -2 is -8 plus 8 is 0. And 4 times -3 is -12 plus 12 is also 0. All right. And so basically, I've got my, I've got a pivot position here. Oops, let me do that. Pivot position here, pivot position here. So my matrix is in echelon form. Right. Remember the rules, zero out below the leading entries, all leading entries to the right of the one before it, and any rows of zeros are at the bottom. So we satisfy all that. So, so the first question, remember from the last time, first question that you want to ask is the system consistent? So is this system consistent?
Yes.
Yes, and we know that because why?
The last row is not in the form of all zeros, and then the augmented not a 0.
Exactly. So there's no row of this form, no row of that form. We kind of get close, right? We got a row of all zeros, but over here it's 0, so that's fine. So, so number 1, is the system consistent? Yes.
I have a question.
Yep.
So when you're trying to get it into echelon form, and like in that that second matrix there where it's 1, -7, 0 on the top. So if you go right 1 and down 1 and it's a 0, you just move right in that same row to look for a new leading coefficient?
Yeah, because you want you want your leading entries, you want to have one in each row if you can. And if you couldn't have one in a particular row, then that would mean that row's all zeros, or well, at least in the coefficient part, it would be all zeros because you couldn't find a leading entry. So yeah, so you just basically want to go down to the next row, move over, if that, down to the next row, move over, not a non-zero there, so keep going. Well, actually, I mean, if this was a non-zero, you'd want to swap rows to move it up here. But since these are both zero, then there's nothing we can do in this column. So we move on to the next column.
Okay, thank you.
Yep. Okay, so so we know, is the system consistent? Yes, it is. And then the next question is unique solution or infinite. And the answer, I don't think we specifically talked about how you answer this. So let's talk about that just a little bit. So so once you get your matrix in echelon form, the columns, we kind of separate the columns into two types. So when we get a matrix in echelon form, we separate the columns. Remember, columns correspond to variables into two types. Okay, so one column with a leading entry. And this leading entry, we're going to call that a pivot position. So, but a pivot position, it's a little bit kind of wordy here, but basically when your book talks about a leading entry, it's talking about the actual number, like in this case, both our leading entries are ones. When it talks about pivot positions, it's actually talking about the position in the matrix, not the actual value in the matrix, but the position. So when I talk about pivot positions, I'm talking about this spot in the matrix. This would be the first row, first column, and this one is second row, third column. But sometimes I'll kind of use those terms interchangeably, but they actually, there is a distinction. But we want to look and see, where are the columns that have leading entries, or where are the columns that have pivot positions? And these are said to be basic. All right, basic. And typically we say that that variable is basic. Basic. The variable in that column is basic. The other one, columns without a leading entry or pivot position. These are said to be free. And again, we refer to the variable as free. All right, so we've got basic variables and free variables. When system, let me back up. When a consistent system has free variables, has at least one free variable, it has an infinite number of solutions. otherwise a unique solution. I'll let you catch up with that.
Okay, so then this is pretty much just saying that if there's an extra free variable, like that second zero in that
Mhm.
second row,
Mhm.
then it's going to be, what do you call it? It's going to have an infinite number.
Yeah. So if we look at this matrix, and you do this when you have the matrix in echelon form. So these two columns have leading entries or pivot positions. So they're said to be basic. The variables corresponding to these columns are basic. But there's no pivot position here, so that's a free variable, and no pivot position here, so that's a free variable. All right. So the fact that this system has free variables means that there's an infinite number of solutions. But you only arrive at that conclusion after you've asked question one. So you first need to ask, is the system consistent? Then if the answer is yes, then you look to see if there's free variables or not. Okay. All right, so this system has free variables. In fact, the problem in the book wouldn't say write the general form of the solution if it didn't have free variables, but nevertheless, this is how you make that determination. So we're asked to write the general form of the solution. So let's talk about how to do that. And let me see if I can just paste that down here. Okay, so let's go back to work on this. So the solution here, the way we write it is we just we look at well, here's my approach. So I just write down the what the matrix says. So that first row says x1 minus 7x2 plus 6x4 equals 5. So remember that's x1, x2, x3, x4 column. And from row 2, I get x3 minus 2x4 equals -3. All right, so that comes from row 1, and that comes from row 2. Then I want to just solve. I want to solve for the basic variables. All right, so that means x1 is one of my basic variables. So x1 is equal to 5 plus 7x2 minus 6x4. And x3 is equal to -3 plus 2x4. And then we add that x2 and x4 are free. And that's the solution. Or general form of the solution. So basically the idea is that x2 and x4 are free variables. So you give me values for those, and then I'll tell you what x1 and x3 have to be. All right. Questions here?
You just keep this up for a second.
Sure. Yeah, and then I mean, I'm happy to do that now, and I'll also post these notes after class today and post a video. But the general form that you want to keep in mind here is you want to have, basic variable equals some expression involving constants and free variables, but no other basic variables. All right, so this is a basic variable. There's constant, free variable, free variable. Basic variable, constant, free variable.
Could you explain how x, the second one, is a free variable?
X2.
Yeah,
Yeah, because there's no pivot position or no leading entry in that column.
so for it to be a basic variable, there should be a number where that second zero is.
Yes, yes. In which case that wouldn't be a leading entry. Yeah, all you do is look, where are my leading entries? So the variables corresponding to those columns are basic and all the other variables are free. All right, other questions? Okay, I think I'm gonna leave that there and move on. Whoa. Really does not like when I move my cable. Okay, I'm gonna move on to section 1.3 now. All right, so section 1.3, the title is vector equations. So the first thing we're going to do is talk about what's a vector. Let's see, I don't know if your book has a definition. Well, they say ordered list of numbers, but essentially a vector is a one-dimensional matrix, right? So like, we look up here, right? This is the matrix, but if we just took one column out of that matrix, that would be a vector. So just either one column or one row, because that would be a one-dimensional slice of a matrix. So that's what we refer to as a vector. And typically, for our purposes, we're really most of the time interested in just columns. So we're going to talk a lot about the columns of a matrix, and generally think of a vector as a column vector, where it's one-dimensional as a column as opposed to a row. All right, so so a vector, for example, x equals 3, 2, that's a vector. Or x equals 6, -8, 4, 1, 10, that's a vector. So vectors can have different sizes, and the one thing that really comes through in this section is that vectors have a geometric interpretation. So a vector, we can draw vectors in that have 2 dimensions, or 2 entries. So for example, like this vector 3, 2, it looks like this. So if I go 1, 2, 3, 1, 2, right? We know how to, right? That's the point, right? From algebra, we know that's the point 3, 2. But that point defines the vector 3, 2. So that vector, or that ray, if you want to think of it, that starts at the origin and goes to the point defined by the numbers in the vector. That's what we refer to as a vector. So there's some things that we can do with vectors, some operations we can perform on vectors. In your book, they talk about these on, let's see, there's a green box on page 29 in my book in section 1.3. Before I talk about that, let me just say, let me back up just a little bit. So you may have in some class been introduced to the notation, maybe you have a bold R like this. Anybody familiar with that notation?
Is that like all real numbers or?
Yes, that's exactly what it is. Yes, this is the set of real numbers. So, so what's a real number? Not a trick question. It's like, there's not like alternative fake numbers.
A number that's imaginary.
What?
A number that's not imaginary.
Yes, we do have imaginary numbers, and those are not real numbers. Correct. So the set of real numbers basically are numbers that are not imaginary. That's a good way to put it. But they include the integers. They include fractions. They include decimal numbers. So if you're a computer science type, you can think of this as floating point numbers on the computer, although, you know, some numbers can't be represented exactly. So we don't, floating point numbers on the computer are not exactly the whole set of real numbers, but it's that idea. So we use this letter R, capital R, to represent the set of real numbers. And then we kind of play off that, and we use like R2. And this is like the set of all two-dimensional vectors, whose entries are real numbers. Right, so this is, so if we wanted to be very proper, we'd say this is like the set of all like A, B, where A and B are real. All right, so things like 32, 4/5, -8, pi over 2, -e. All right, those are all vectors in R2. All right, so to be in R2, it just means that you're a vector with two components, and the two components are real numbers. All right. Questions here? All right, so what do you think R with a 3 is?
Three-dimensional vectors.
Yeah. I mean, extrapolate from the previous one. This is set of all 3D vectors whose entries are real numbers. Yeah, so for example, 1, 2, 3, -7/10, 42 pi. All right, so three-dimensional vectors. Three-dimensional means it's got 3 entries. And then in general, we talk about Rn, And Rn is the set of all n-dimensional vectors whose entries are real numbers. Okay, so, and this just means, you know, you have to know what n is to be able to talk about this. But a lot of times in this course, we'll talk about Rn in general, and basically with the understanding that n could be any positive number, right? Any positive counting number, 1, 2, 3, 4, 5, whatever, right? So this is, it's probably a good place for me to point out that particularly with chapter 1, the biggest obstacle to students being successful with material in chapter 1 is getting used to the vocabulary and the notation. So, so I advise you to like maybe keep a little, you know, page in your notebook, or, you know, document somewhere where you like write down definitions and you know, like examples like this, just to refer back to, even you know, terms like free variable, basic variable, consistent, inconsistent, all those terms. There's just a lot of them in chapter 1, and so being able to have a quick reference to look at is I think is probably valuable. And that's another reason to really try to stay on top of the homework, because doing the homework problems forces you to engage with that vocabulary, and that's it. You just have to become familiar with it, and you become familiar with it by using it. And the most obvious way to use it is to do homework problems where you have to use it. All right, so but for now, let's go back. We're gonna talk about R2 for just a little bit. So, well, actually, before we talk about that, let's talk about some operations on vectors. All right, so so there's two main ones that we're going to be using. One is addition, so adding two vectors together, and so I'll just show you in R2. So if I have a vector AB and a vector CD, then when I add them together, I just add the components, the numbers that are in the same places together. So it's just A plus C, B plus D. Okay, so for example, if I have 5, -4 plus 13, 10, what do I get? I get, you know, 13 plus 5, that's 18, -4 plus 10 is 6, right? So that's how that works. Or, you know, I could have, this works no matter how big your vectors are. So if I had like, you know, 1, 2, 3, 16 plus 4, -2, 5, 1, right? Still same idea. 1 plus 4 is 5, 2 minus 2 is 0, 3 plus 5 is 8, 16 plus 1 is 17. So you just add whatever numbers are in the same position, just add those together. Okay. The other operation is what we call scalar multiplication. Okay, and so this means multiplying a vector by a number, a real number. Okay, so for example, so if I have, let's just say, I'll just do a real example here. So if I say I want to multiply 2 times -8, 10, then that's 2 times -8. So -16, 2 times, it's supposed to be a 10, that's 20. So you just multiply each element by that scalar. So we call this is our scalar. So I'll use that term scalar fairly frequently. So it's just the math way of saying a number. Just a single number as opposed to a vector. Okay. All right. Couple more things I want to hit. Where are we on time? Oh, I'm moving my cable, so this is okay. Are we back?
Yep, we can.
All right. Okay, so let's see. All right, so let's talk about some vectors in R2. All right, so I don't even know if I said that back up here, but like this, when we say that, we say R2, and this is R3, and this is Rn. All right, that's how we say that. Okay, so let's just take a couple of vectors in R2. So this is our example. So let's just take a couple of vectors. Say, let's go back and take R3, 2, and so let me draw that. Again, 1, 2, 3, 1, 2. All right, so that's that vector. Let's do another one. Let's say, how about, I'm going to stay in the first quadrant. So I'm going to do, say, 1, 4. So that's going to appear. My drawing's not the best, so bear with me. But so this is 3, 2. That's the vector 3, 2. This is the vector 1, 4, and that's what they look like. Since we just learned how to add vectors together, let's see what 3, 2 plus 1, 4 is. So remember, to add vectors, we just add the elements in the same position. So we get 3 plus 1 is 4, 2 plus 4 is 6. All right, so that's 4, 6. So if I go 1, 2, 3, so there's 4. And if I keep going up here, there's 5, 6. So, that looks something like so these are slides I prepared for my online class. Can everybody see that? It says a graphical look at vectors.
Yeah, we can.
Okay, so let me see. So let me just, all right, so basically this is what we were just talking about. This talks about Rn, right? So here's what a vector in Rn looks like. Basically just means it's got n entries in the vector, and each one of those is a real number. And similarly, R2, R3, just examples. And then we talked about operations on vectors. So let me skip through this. Okay, so here's where I was getting to when my iPad decided to die on me, or the connection died. So here's a couple of vectors, right? Here's 2, 1 and 1, 4. Actually, these pictures will be prettier than the ones I could draw freehand. But 2, 1, right? So that is go out 2, up 1. That ray or the line segment from the origin out to that point, that is the vector u, and similarly here's v, which is 1, 4. And so as I was about to do, I was going to add the two together that I had written, and so that's what I'm doing here, right? If we just add 2, 1 and 1, 4, that's 2 plus 1, you get 3, 1 plus 4, you get 5. And then if you draw that out, right, so you get 3, 5. So if we come over 3 and up 5, we're at u plus v. Now, some of you, if you've had physics, you might be familiar with the parallelogram method of adding vectors. And basically what that does, can you guys see my mouse?
Yeah. we
Yeah.
can.
Yes. Okay, good. Because otherwise I'm pointing at stuff and it's not making any sense to you. So the parallelogram method says, okay, if you want to add u and v, these two vectors, then go to the tip of each one and draw a line that's parallel to the other one of the same length. So this green line is parallel to v and the same length. And this green line up here is parallel to u and the same length. And then those lines intersect, and where they intersect, that's the sum of the two vectors. Okay, so that's why it's called the parallelogram method. You draw that, you complete that parallelogram, and then the diagonal across that is the sum of the two vectors. All right, so keep that in mind. And then the other thing that we talked about was multiplying a vector by a scalar. And yeah, the word scalar, what you can kind of think about from that is the idea of scaling a vector. And when we say scale a vector, we mean either like extend it out or shorten it. So we scale it, we add or we multiply it by some number to make it longer, make it shorter, make it go the opposite direction, whatever. All right, so here I did a couple of examples. I had 3 times u and a half times v. So I think you can figure out how to do that. But graphically, what does that look like? Well, 3 times u, right, is 6, 3. So if we plot that out, what it turns out to be is another vector that goes in the same direction as u, and it's just 3 times longer, right? It's basically taking u and then another u and another u. You can think of it as u plus u plus u. You're adding, u 3 times. And so it's just always when you scale a vector, you get another vector that's in the same direction or the opposite direction, but it's along the same line. Similarly for v, if we take half of v, that turned out to be 1/2 2. And if we plot that, right, here it is, and it's just half of v. It's just when you say 1/2 v, that's what you would expect. It's a vector that's in the same direction as v, but just half as long. All right. So what if we add those two together? So if we add 3u and 1/2 v, we can again visualize it by the parallelogram, right? So you can visualize here we go out to a half v, and we draw a line out parallel to 3u, and do the same thing, go to the end of 3u and draw a line that's parallel to 1/2 v, and look at the diagonal across that parallelogram, right? And so that's what we get. And clearly we can do it analytically also. But the idea that I want you to get from this is that I can scale u, so I can multiply u by something, and I can multiply v by something, and let's assume we're going to multiply by positive values. Could be fractions like a half, but going to be positive values, right? So whatever I multiply by u, I'm getting something, you know, that's along this line here. And whatever I multiply by v, I'm getting something that's, you know, along this line that goes through 0 and v. And so you can imagine that if you just like pick any multiple of each of these and then add them together, you're going to get some vector that's kind of in this area, right? Something, if you think of u and v as defining a cone, like an ice cream cone, right? So we go out all the way this way with u and up this way with v, then we end up with like this ice cream cone shape here. And so we can multiply u and multiply v by whatever we wanted to generate any vector in that's within this cone. And we can't get outside this cone, at least not by using positive multiples for both. But as long as we use positive multiples for both, we generate any vector we want in this cone. I think I have a picture of that. All right, so that kind of gives you the idea there. That if we pick multiples, so we're doing something times u plus something times v, and if we pick those to be positive or at least non-negative, then we generate this cone that's starts out in between those, right, and just keeps getting bigger and bigger, just like a cone does. But there's nothing that says our multiples have to be non-negative, right? Scalars can be any real numbers. All right, so I said, well, what if we take negative multiples of u and v, right? So we do c times u plus d times v, but we assume that c and d are both negative. And so the best way to think about this is to think about looking at negative u and negative v, and then what do we get if we take positive multiples of negative u and negative v? At least that's the way I think about it. And if you look at what negative u would be, right? So negative u, positive u went out like this, and negative u just negates the elements of u. And so negative u comes back, you know, looks like this guy right here. And negative v looks like this guy right here. All right, so it's going to be, instead of 1, 4, it's -1, -4. And again, if we think about taking positive multiples of those two vectors, then we generate this cone again. Except now it's the cone defined by negative u and negative v. Does that make sense? All right. But again, there's no rules that say that c and d have to both be positive or both be negative. We can take a positive multiple of one and a negative multiple of the other, right? So like if we look at this yellow part right in here, it's defined by the vector u and the vector negative v, right? Here's u going out here, here's negative v coming back here. So anything in this yellow area here, we get by multiplying u times some positive number and v times some negative number. And similarly, if we look across over here in the upper left, that's defined by positive multiples of v and negative multiples of u, right? We can generate any vector back in this area. So, the net result of this is that u and v are, in a sense, representative of all vectors in R2 or all vectors in the plane, because I can do what we call generate I can generate any vector in R2 by taking a multiple of u and a multiple of v and adding them together. Does that make sense? I got one thumbs up there, at least one. All right. So what that concept is important because it means that this is a new term. It means that these two vectors, u and v, span R2. Okay, so span is a very important concept in linear algebra. And so spanning these two vectors span R2 because any vector in R2 can be obtained from these two just by multiplying each by some constant and then adding them together. I'm about out of time here, but yeah, and I think you know what, I'm just going to stop here. We still got a little more of section 1.3 that we need to talk about, but I don't want to. I got 3 minutes left, so I'm not going to start anything more at this point. We'll pick it up in class on Monday. So for Monday, we're going to have a quiz. We'll still talk about section 1.3. We'll finish that up. And depending on time, well, class Monday, first order of business, I'll answer any questions you have from sections 1.1 and 1.2. Second order of business, we'll finish up section 1.3, maybe even get started with 1.4. And then the last, say, 20 minutes of class, we'll have quiz that will be on sections 1.1 and 1.2. Stop share. Okay, so let me look. All right. Yeah, so quiz will be 1.1 and 1.2, not 1.3. And I'll post that on the Canvas homepage also. Okay, so any questions before we adjourn?
What did you say about 1.4 something on Monday? Or
I
just
said
1.3?
depending on how time goes, we might start 1.4 also.
Okay.
I mean, we're mostly through 1.3. In fact, you could probably start working on some homework in 1.3. There's just I haven't totally finished it up, so I won't put that on the quiz. All right. Okay, well, thank you all for spending this time with me, and I look forward to seeing you in person on Monday. All right. Bye, everybody. See you next week.
Bye.
Later.
Bye.
Bye-bye.
I do have a question though.
Okay.
It's about, can you go back to the slides?
Sure. Let me